This is a two-dimensional collision. Pause it right now and read this problem and just kind of digest it a little bit. This diagram shows pre-collision, post-collision, the before and after. Obviously, this is a glancing collision, you'll sometimes see it called. You have this gray mass that's going to collide with this stationary white mass. And then they go off at angles, and the angles are given. What we're going to do here is break this down into momentum vectors. Everything I've drawn here is a momentum vector. It is not a velocity vector, and it should also be pointed out these are not necessarily in proportion in any way. I'm just trying to draw these to make a point. This represents the momentum of this incoming gray mass, and this represents the momentum of the outgoing gray mass. This represents the momentum of the outgoing white mass. You can see that it doesn't match those theta 1, theta 2. None of this is necessarily to scale, but I want to make a point. And the point is, and kind of a broader point first, the broader point is don't lose the forest for the trees. See the big picture. See the overall structure of this problem. You will get lost in the math if you're trying to memorize details. The overall structure of the problem is that momentum is still conserved. Momentum is a vector. So this vector is equal to the sum of these two vectors. And I can prove that by lining these up tip to tail. And you can see that that is the resultant. This vector plus this vector really does equal this vector. Now, we're going to do a lot of component analysis. So one way you could look at it is that if we add up all these four components, it equals that. So if I take this component of the final momentum plus this final momentum component plus this final momentum component plus this final momentum component, it equals the total. And if you're really comfortable with your geometry, you can actually solve the problem entirely with a geometric view. I'm going to take a little bit of a hybrid geometric and algebraic view. The main principle here is still the same. Total momentum is conserved. And it's important to remember total momentum. In this case, the total momentum is going to be just for this gray mass right here in the beginning. And because there's no momentum due to this thing. But the two really key equations are P total x equals P total x prime. And when I say P total x, I just mean the total momentum before, and the prime here is indicating after. I hope the pointing with the mouse is showing up nicely on the video. And of course, P total y equals P total y prime. The total, we're going to look at this separately. You've got the horizontal momentum here. You've got the horizontal momentum here. And the vertical momentum here. This is conserved and this is conserved. That's not necessarily obvious. You may not have realized that conservation of momentum allows you to look at them separately, but it does. Here's the solution. I've got this for reference, and pretty much every variable you're going to see that I write out in an equation is going to relate to a vector or some vectors in there. So I'm going to explain every single one of these vectors here. Just check something. I want to make this translucent. So hopefully this will allow me to point to things easily. So let's look at this one here. This is P1x. Then we're going to look at the horizontal. P1x is not the total horizontal momentum. It is this vector here. It is the total, it is the momentum of 1 and 2 mean the pucks. So this is the momentum of the first puck coming in. Well, we know that it's got to be equal to the total of P1x prime and P2x prime. So this right here is P1x prime, and this right here is P2x prime. So what this whole equation is saying is that this vector plus this vector equals this vector. It's also just another way of saying the total momentum in the horizontal equals, in the beginning, which is this, equals the total momentum in the horizontal at the end. And of course, pause and stop and rewind and digest this equation, because if you don't understand this equation, you're not going to be able to write it. So it means the total momentum in the horizontal before, which is just due to that 1, is equal to the total momentum in the horizontal after, which is the sum of two components. And as soon as I say components, hopefully that makes you think, oh, okay, we're going to do some sines and cosines. And don't worry about this blue arrow for now. That's just going to represent how I'm going to be plugging something in later. So this is P1, which is going to be really easy to calculate. We sort of set up our coordinate system so that that'll be easy to calculate, because we've set up a coordinate system where this air puck moving at 2 meters per second, we're going to call that horizontal. So that's going to be easy to calculate. This is a little tricky. This is literally this quantity here, not the total, but this right here. We're just expanding that, and we're writing P1 prime cosine 32.5, because that's the x component. And then we're going to expand this right here, will be expanded to this, P2 prime cosine 44.6. Those are the x components. That's this, and that's this. Now, it's good to go over and look at the y components. Let's start setting up the y. What I've done is a little bit of a shorthand here. Taking a little bit of a liberty, and I'm saying, well, really what we're saying is that this vector equals this vector. This is where I'm taking a little bit more of a geometric approach. I'm not worrying as much about negatives. You'll see that this will all work in the end. But basically I'm saying the y, the P1y, which is this piece here, prime, equals P2y prime, because this is a consequence of the fact that they have to equal 0, because there's no y momentum in the beginning. So naturally we're going to write those out as components. And so P1y expands out to be simply P1y prime is P1 prime times the sine of 32.5. And the P1 prime is actually this vector. Now we're taking the component of that, so be careful with that. And then of course P2y prime expands out to become this. So really what I've done now is I've written out some equations, and I've kind of isolated, and I've written two equations with two unknowns. And you may be saying, well, I see three unknowns. No, that P1, I'm just trying to keep this a little not quite so messy, but P1 is basically a known quantity. That's very important. P1 is a known quantity, because look, we have a 1 kilogram air puck moving at 2 meters per second. So P1 is 2 kilogram meters per second. So that's just a known quantity. Now I can rearrange this equation so that P1 prime, I'm writing P1 prime in terms of P2 prime, and it's this quantity. Be careful with your signs here. This expression, just mathematically make sure you're doing the sign of each before you do that quotient. And now that whole quantity, which I'm bracketing here, this whole quantity will get substituted here for P1 prime. You plug, you chug, and you can get P2 prime can solve for P2 prime, because now we'll have an expression that's in terms of P2 prime. You do the algebra yourself. And we get a momentum. To get the velocity, that's easy. You divide by the mass. And V2 prime is 0.735 meters per second. You plug back into this. This is similar to what we did for elastic collisions. Plug back in your P2 prime value in here. And you'll have, plug it in here, P2 prime value, it's over there. And you'll have P1 prime, and that ends up being 1.44 kilogram meters per second. And now we can get our final answer for V1 prime by dividing by the mass of V1 prime. So to summarize, don't lose the forest for the trees. Remember, I took a pseudo-geometric and algebraic approach, a hybrid of the two. It's all based on the fact that P total x equals P total x prime, P total y equals P total y prime.